Welcome back to the lecture videos for Calculus 2. Section 7.2 in your textbook covers lots of vitally important information. So we're going to divide section 7.2 into three subsections, 7.2A, B, and C. Overall, we're going to study derivatives and integrals involving natural logarithms and natural exponential functions. This information is vital to your success in this class, in Calculus 3, and differential equations. So please study this diligently and practice a lot. We'll begin our approach to finding the derivative of a natural logarithm with a problem. Can you determine the integral of 1 over x dx? Looks like a very basic Calc 1 problem, and you might think to rewrite it as a power of x and then apply the power rule for integrals. Recall that the power rule for integration is given by integral of x to the nth power dx equals x to the n plus 1 divided by n plus 1 plus c. Now, if I try to apply the power rule to this particular problem, and I add 1 to the exponent and I divide by the same value, do you see the problem? We end up with a 0 in the denominator, or an undefined function. So the power rule comes with the stipulation A for all n not equal to -1. By the way, this is a symbol you may not have seen before. This upside down A represents the phrase for all. You'll see it quite a bit in our notes here. It's called the universal quantifier. It just means for all n not equal to -1. So I can apply that power rule for any exponent but -1. However, the fundamental theorem of calculus says that we can find an antiderivative for any continuous function, and 1 over x is a continuous function. Thus, the problem, integral of x to the -1 dx, is defined as a special case. The function natural log of x is defined as the integral from 1 to x of 1 over t dt for all x greater than 0. It has the domain 0 to infinity and range -infinity to infinity. Now, if you just look at the algebraic part of it, right, or what you learned in algebra, the domain and range of the natural logarithm should be familiar. We're just defining the natural log function in terms of a definite integral. Now, by the fundamental theorem of calculus, as we saw in the last section, the derivative with respect to x of natural log of x is the derivative of this integral. And remember, the combination of a derivative and integral together really doesn't get you anywhere. We end up, if you'll recall, with the integrand. So if we sort of shortcut this formula, we end up with the basic rule: derivative with respect to x of natural log of x is 1 over x. It's a very simple formula, but very fundamental and important. We'll use this formula all the time. The derivative with respect to x of natural log of x is 1 over x. Now, we're not always just going to encounter natural log of x. We may encounter natural log of u, where u is some sort of function of x. So we'll have to apply the chain rule. In this case, we're going to differentiate starting with the same pattern. That is, we're going to do 1 divided by the argument of the natural log, but then we're going to multiply by the derivative of the argument. Let me write it like this: 1 over u times du over dx. Or another way to think about it is the derivative of the argument divided by the argument itself. And again, the argument refers to what's in parentheses. So let's apply this formula to several examples. We're simply going to find the derivative of these natural logarithmic functions. The first one is the derivative with respect to x of natural log of 5x. Notice the argument is a function of x, not just an ordinary x. So we're going to take the entire argument and put it in the denominator, and in the numerator, we're going to multiply by the derivative of that argument. The derivative of 5x, of course, being 5. If we simplify, notice we get 1 over x. It's a very simple process. Let's try example B. The derivative with respect to x of natural log of 4 minus 3x squared. Remember, the practice is to take the entire argument and put it in the denominator, and the derivative of that argument goes in the numerator. The derivative of 4 minus 3x squared would be negative 6x. Now, in this case, I cannot reduce the fraction, but I can simplify it a little bit. Notice if I factor a negative 1 out of the top, and I'm going to factor a negative 1 out of the bottom, those two negative 1s would cancel, and I'd end up with 6x over negative 4 plus 3x squared. Or to make it more readable, we can put the positive number first in the denominator, and we end up with the derivative 6x over 3x squared minus 4. Now observe that pattern. Look from start to finish. Notice I changed the sign of the numerator and I switched the order of the terms in the denominator. When we switch the order of terms in that denominator, it cancels out a negative 1. So remember that as a shortcut to simplification. Moving on to example C, the derivative with respect to x of natural log of x to the fourth. Notice the argument here, what's in parentheses, is x to the fourth. So we take the entire argument and put it in the denominator, and we find the derivative of that argument, 4x cubed, and put that in the numerator. We could reduce and cancel out an x cubed here, and the resulting simplified derivative is 4 over x. One thing that you should be aware of here, when you differentiate a natural logarithmic function, the derivative does not have a natural log. It turns out to be, in this case, a rational function. Now, compare example C to example D. They look very similar, but notice in example C, the exponent was on the argument, and in the case of example D, the exponent is between the natural log and the argument. This indicates that the entire natural log function is raised to the fourth power, not just the argument. So to clarify that, let me rewrite it like this. The derivative with respect to x of natural log of x, all raised to the fourth power. That is basically equivalent notation. So to find the derivative, observe that we have a function of x raised to a power. This calls for the chain rule. So we're first going to begin by applying the power rule. We're going to take the power down in front as a coefficient. We're going to keep the base the same, natural log of x, and we decrease the exponent by 1. The chain rule then tells us to multiply by the derivative of the argument, which in this case we have learned the derivative of natural log of x is 1 over x. Now let's be sure and write this in the cleanest, simplest presentation. One thing that we can do is take the natural log of x raised to the third power, and we can move that power between the natural log and the argument. So we could write this as 4 natural log cubed of x, and if we multiply that by 1 over x, we can simply put the entire thing over x. So that is a simplified derivative. Also, if you prefer the fraction notation, you could write it as 4 over x times natural log cubed of x. That's also acceptable. Make sure that when you present the derivative, it is always in simplified form. So those two examples are two very good, excellent examples to study, and it teaches you to be sensitive to the placement of the exponent. Is it on the argument or is it on the entire log function? So make sure you know how to handle both of those instances. Example E, the derivative with respect to x of x squared natural log of x. Notice we have the product of two functions of x, so this requires the product rule. So we have reviewed the power rule, we have reviewed the chain rule, and now we have the opportunity to review the product rule. So we've got two functions of x. I'm going to move my derivative here on the next line. The pattern of the product rule, if you'll remember it this way, it'll help you with the quotient rule as well. It's same times derivative plus derivative times same. If you remember it in that order, it matches the order in the quotient rule, and it helps you to set your quotient rule up right. I hope that's how you learned it in Calculus 1. So we're going to take our first function and keep it the same. Then we're going to multiply by the derivative of the second function. The derivative of natural log of x we learned is 1 over x. Plus, now we're going to do the derivative of the first function, which is 2x, plain old power rule there, times the second function as is. Same times derivative plus derivative times same. Now, if you reverse the order of these two factors, it is still absolutely correct. Again, I present it in that order because it seems to help students with the quotient rule. Let's go ahead and simplify. X squared times 1 over x is x, plus 2x natural log of x, which is a simplified form of the derivative. However, if I asked you to determine if the original function was increasing or decreasing, or if I said find the critical points of the original function, you'd probably set it equal to 0 and start solving for x. And the first thing you would do is to factor it, right? So I'm going to go ahead and factor this. X times 1 plus 2 natural log of x. That's probably the best presentation, although either one is acceptable, either the multiplied out and separated form or the factored form. So what do you think so far? Is section 7.2a a little easier than section 7.1? I think so. It's just learning a formula and practicing that pattern. Let's try the next one, the derivative with respect to x of natural log of x. So we have the composition of two functions. So again, we're going to need our chain rule. So the chain rule says that we're going to differentiate the outside function. So I have natural log of something, right? To differentiate a natural log, we take the argument of that function and we put it in the denominator, and then we multiply by the derivative of that argument, or we have the derivative of the argument in the numerator. So that's the derivative of the outside function. But now we need to multiply by the derivative of the inside function, which is 1 over x. The chain rule says we're going to differentiate the outside function first while keeping the argument the same, and then we're going to multiply by the derivative of the inside function. If we think of the inside function here as u, then the pattern of our derivative is going to be 1 over u times du over dx. So 1 over the argument times the argument's derivative. If I want to simplify that, I might call it 1 over x natural log of x. Very simple application of the chain rule. Now, one thing you may have thought to do back up here on example C is to apply a logarithmic property to simplify the function before you differentiate it. If you thought that, that's pretty impressive. That's what we're going to be doing on the next few examples. Tip: use logarithmic properties to expand complicated logarithms before differentiating. So looking at example A, if I find the derivative directly, I'm going to end up with a rational function in the denominator times the derivative of a rational function, which would require the quotient rule. Not that we couldn't do it, not that it's impossible, but it is tedious. So before we find the derivative, we're going to expand this expression using logarithmic properties. Now let me write the 3 basic log properties that you need to know up here across the top. So we may have log with any base, and we've got the product of 2 factors in the argument. If we have a product in the argument, we separate this into the sum of 2 individual logarithms. Each factor gets its own logarithm. And by the way, I used log base b here, but we're going to apply this to natural logarithms. So instead of log base b, you could certainly have a natural log ln there. Now, in addition to our product rule, we've got the quotient. Let me do log, be consistent. We've got the quotient rule for logarithms, not the quotient rule for derivatives, but how do I handle the quotient in the argument of a logarithm? We'll take the logarithm of the numerator minus the logarithm of the denominator. And the last one is the power rule for logarithms. Let's suppose I have some sort of power on the argument. Well, log properties tell us we can move that power down in front as a coefficient, and that's equivalent to having a power on the argument. Those are the three basic expanding and condensing properties that you'll need to know. So back to example A, notice I'm not going to differentiate this function. I'm simply rewriting the function by expanding it with log properties. So I'm not going to label that left side as f prime. So if I expand this with the quotient rule, we're going to have natural log of the numerator minus natural log of the denominator. Now remember, you cannot distribute a natural log across a sum or a difference, right? So be very careful about that. Now that I've separated the logarithms, I'm ready to find the derivative, and I'm going to indicate that I'm changing from f to f prime by actually labeling that left side as f prime. Now we can differentiate term by term. Differentiating natural log of 2x, we're going to take the entire argument and put it in the denominator, and we're going to have the derivative of 2x, which is 2, in the numerator. Now, the derivative of the argument x plus 3 goes in the denominator, and its derivative, which is 1, goes in the numerator. So if we reduce here, we have 1 over x minus 1 over x plus 3. That's a perfectly acceptable derivative, but again, if I needed to analyze the derivative, I would probably want those combined with a common denominator. So I'm going to go ahead and take the time to do the algebra and combine the fractions. So our common denominator here is x times x plus 3. Looking at the first denominator compared to the new one, we've gained a factor of x plus 3. So I'm also going to multiply this numerator by x plus 3. Again, looking at this old denominator to the new denominator, we've gained a factor of x, so I'm going to multiply that numerator by x as well. So just combining fractions with a common denominator here. Notice x plus 3 minus x leaves behind 3 over x times x plus 3. This is really the best presentation of the derivative. Again, if I wanted to analyze it, look for vertical asymptotes, something like that, I would need it in that combined form. Now, if we go back to the original problem, if I had differentiated that directly without expanding with log properties, I would have ended up with the same thing. It just would have been a little more challenging to get there. Next example. G of x equals natural log of the cube root of x squared over 3x minus 5. Now really think about what would it take to differentiate this directly. I'm just going to kind of scratch it out over here. We would do 1 over this big, lovely, complicated argument times the derivative of that argument. What's that going to look like? Well, I'd have to start with the power rule. Think about that cube root of x as x to the 1/3. And then I'd have to multiply by the derivative of this, which would require the quotient rule, right? Same times derivative minus derivative same. And then I would need to simplify that. That is yuck, right? It's definitely possible but not convenient. So let's take advantage of logarithmic properties. Let's expand and then we will differentiate. So notice here I am not differentiating, so I'm going to label this g of x. Understanding that the cube root of x is the same thing as a 1/3 exponent, right? And applying the power rule for logarithms. Remember, if I have an exponent on the argument, I can move that down in front as a coefficient. So notice I'm moving that exponent 1/3 down to the left, not because I'm differentiating, right? I'm not doing the power rule for derivatives here, but because I'm doing the power rule for logarithms. So I'm not yet doing calculus, I'm still doing algebra. Now I can expand this logarithm by taking logarithm of the numerator minus the logarithm of the denominator. However, I've got to be careful here. Since 1/3 is multiplying the cohesive logarithm, 1/3 has to multiply the split logarithm as well. Now, I'm even going to take this a little further and move this exponent down to the left to join that coefficient that's already there. And then watch how simple our differentiation is going to be. So here's our expanded function. Now I'm going to actually differentiate. So we're moving on to the calculus part, right? Differentiating term by term. The derivative here is going to be 2/3 times the derivative of natural log of x, which is just 1/x, minus 1/3 times, for this second term, we're putting the 3x minus 5 in the denominator and the derivative of that argument in the numerator. Now, look how beautifully this simplifies. We have 2/3x minus 1/3x minus 5. Now, I am going to put in the effort to combine those two fractions to a single fraction, but believe me, it's going to be much easier than the algebra that would be required to simplify the original approach. So let's go ahead and combine here. Our common denominator is 3x times 3x minus 5. The numerator here is 2. We multiplied that denominator by 3x minus 5, so we'll gain one of those factors in the numerator, and this guy's going to get a 3x. So let's simplify. G prime of x then is going to be 6x minus 10 minus 3x divided by, I'm going to leave this factored because it makes it easier to observe domain, critical values, asymptotes, that sort of thing. So our final answer then is 3x minus 10 divided by 3x times 3x minus 5. So hopefully you can see from this example that applying log properties first, doing a little algebra to simplify the function, will really simplify the differentiation process. All right, let's throw some trig functions in there. Let's find the derivative of h of x equals natural log of the absolute value of cosecant of x. Now let's rewrite cosecant of x as 1 over sine of x. Then I can split this up with log properties, natural log of the absolute value of 1 minus natural log of the absolute value of sine. Natural log of 1 is equal to 0, so I end up with negative natural log of the absolute value of sine. Now I'm ready to differentiate. So we're going to denote the fact that we're doing calculus, we're finding the derivative with h prime of x. So I want to communicate to you here, don't just give me an equals right here and then start doing your derivative, because you haven't indicated that you're moving from algebra to calculus. This, if I differentiate right here, is not equivalent to this. So make sure you label when you start your derivative. So we have a -1 coefficient. We're going to do, I'm going to write -1. We're going to put the argument in the denominator. And by the way, you can ignore the absolute values when you're differentiating. The argument in the denominator and the derivative of the argument in the numerator. What's the derivative of sine? Hopefully you remember that is cosine. We have -1 times cosine over sine. We could simplify that and call it negative cotangent of x. Now, make sure that you notice on the next problem, on example D, I want you to compare example A and example D. On example A, we were able to expand with the quotient rule for logarithms because we have the logarithm of a quotient. In example D, we have the quotient of two logarithms. So there's nothing I'm going to be able to do algebraically to simplify this function before I differentiate. I cannot expand this because the quotient of two logarithms does not simplify, whereas the logarithm of a quotient does. So we're going to have to differentiate directly, applying our quotient rule. So again, we're going to apply the quotient rule, and this is quotient rule for derivatives. So the quotient rule says to take the original denominator and square it. And I'm going to denote that by putting the square between the logarithm and the argument. Then I'm going to take that denominator and lead with that term in the numerator. And then I'm going to follow the pattern, same times derivative plus minus derivative times same. Okay, so I've got the denominator as is. Now I'm going to multiply by the derivative of the numerator, which we've learned is 1 over x, minus, the quotient rule has a minus, the derivative of the denominator. Well, it's a natural log function, so we're going to put the argument 5x squared in the denominator and its derivative 10x in the numerator, times the original numerator. Now let's simplify this just a little bit, and then we can work on simplifying the complex fraction. So I'm going to cancel that 5 into that 10 2 times. And notice the x cancels here with one of these guys down here. So it looks like we're ending up with, I'm going to write it as 1 over x. Well, let's do it this way. I want to emphasize the fractions here. I'm going to call it natural log of 5x squared divided by x minus 2 natural log of x divided by x all over natural log squared of 5x squared. Now, be very aware that we cannot cancel this x and this x, right? They are not compatible. The one on the top is the argument of the logarithm. The one on the bottom is the plain old x. They're not the same factor, so be careful with that. Now, we do have a complex fraction, and the way we're going to simplify it, we're going to multiply the top and the bottom by our LCD, which is x. So when I distribute x to each of the terms in the numerator, that's going to cancel each of those denominators. So we'd end up with natural log of 5x squared minus 2 natural log of x. And in the denominator, we're going to multiply by this little monomial factor x. I'm going to write it to the left to make it readable. That is, it's not going to combine with the argument that's already there. And there's nothing we can do to simplify that, so that is our final derivative. So let's finish this section with a classic Calculus 1 type problem. Find the equation of the line tangent to f of x at 1, 0. Finding the equation of a tangent line is a fundamental problem in basic calculus. So to find the equation of the tangent line, the first thing that we need to do is find the derivative of f. The derivative is what gives us the slope of the tangent line. So we're going to begin by finding f prime of x. Now notice, I can't cancel the x's in the original function, but I do have a square root in the argument. So in fact, before I differentiate, let me call this regular f of x, I'm going to simplify that. Okay, we can rewrite it as x to the 1/2 over x, and then by the power rule for logarithms, I'm not differentiating, right? I can move that power down in front as a coefficient. This gives us 1/2 natural log of x divided by x, or we could call it natural log of x divided by 2x. Now remember, I have not done any calculus. This is still my original function f of x. Now that we've simplified it with log properties, we can go ahead and find the derivative. So I'm going to label the fact that we're changing the function. This is not equivalent to the previous line. This is a new application or new operation. We're going to need the quotient rule, right? So I'm going to begin by squaring the denominator. If you start by squaring the denominator, that helps you remember which factor goes first in the numerator, right? So whatever you square in the denominator, keep that the same for the numerator, and then follow the pattern, same times derivative minus derivative times same. So I've got the denominator as is. I'm going to multiply by the derivative of the numerator, which is 1 over x, minus derivative of the denominator, which is 2, times the numerator as is, natural log of x. So when we simplify, our x's are going to cancel, and we end up with 2 minus 2 natural log of x. Let's go ahead and square our denominator, being careful to square both the coefficient and the variable term. Not quite done yet. We need to reduce. Let's do that by factoring a 2 out of the numerator. so that we can cancel the 2 with the coefficient 4 in the denominator. It's going to leave us with the coefficient of 2 here in our denominator, so we end up with 1 minus natural log of x over 2x squared for the derivative. So the fundamental bottom line that you need to know from this particular section, back up here, the basic rule: how do you differentiate a logarithm, and how do you differentiate a natural log with a function of x as its argument?